The title of chapter 4 is the control and operation of grid-connected DC-AC converter. So at the end of this chapter, you will be able to classify different types of power converter, develop a dynamic model of a grid-connected DC-AC converter, apply control strategy to operate grid-connected converter under different operating condition, and you will be able to design a control technique for injection of different actually power from energy sources to the power grid, and and you will be able to implement technique to compensate the harmonic and reactive power also in power grid, which are somehow connected by nonlinear loads. And also you can adjust the power factor of the grid by integration of energy sources, can be renewable energy or storage devices in main grid. So before we start, do we have any question, comment, concern, or something regarding the previous session? No. Okay, good. So the first topic is the classification of the power converters. Basically, I'm not going to say that this is something that famous as a classification of the power converters. When we are talking about the power converters, is 2-level, 3-level, 4-level, I don't know, H-bridge converter, diode clamp, or flying capacitor, this type of. But here we are going to talk about the grid following, grid forming, and grid supporting converters. So when we are talking about this type of topologies, basically converter can be conventional 2-level converters, depended where we are going to use. It can be also multi-level converters for high power applications. But the control technique we are using shape the operation of this type of converters. So the first category is grid following or grid feeding converters. So does anybody has any idea what is the grid feeding converter? I'm pretty sure that lots of, no? Okay. So this type of converters, yeah, tell me. Yeah, okay. Mm-hmm. You mean that, for example, grid connected? Mm-hmm. Yes. So I mean, this is type of the conversion system that has actually is synchronized with the power grid based on the frequency and voltage, and they are providing electricity for the power grid. So if you have a source of energy, I don't know, 5 megawatt, then you are going to inject maximum active power to the grid. Then you should provide the grid following or grid feeding actually converter. So we have also grid forming converter. So this type of converter is, I mean, the conversion system is better to say, is working like a voltage source. So it has a small output impedance, which also provide the frequency and voltage, maintain the frequency and voltage, and can be used as a reference for the other converters. So you can consider this one like a grid and then the other converter can be connected to this type of conversion system as a slave, and then follow the power injection. We have another type of actually conversion system. It's a grid supporting or grid connected. So in grid connected system is working like the same like a grid feeding or grid following system, but the difference is that this type of technology are mainly for the regulation of voltage and frequency in the grid. So in grid feeding, you provide the electricity and inject to the grid. So it means that you're going to provide the maximum active power to selling the grid. So if you are, for example, private sector that have a small power plant which can provide, I don't know, up to 10 megawatts, and you are going to sell it to distribution grid, you don't care that what is happening in the grid. You have some commitment to inject some power to the grid. So you should use the grid feeding. But when we are talking about the grid connected, it means that you have some problem in your system. So system is, I don't know, the voltage is not regulated, the current is not, the frequency is not regulated. Then you use this technology to provide active or reactive power based on the changes, and based on that you can regulate the voltage and frequency of the system to support the stability of the power grid. So is it clear for everybody? Yeah. Grid support. This grid supporting can be grid following or grid forming, okay? But depended where you are going to use. So basically, they are two different applications, and this one is also support the stability of the grid, but it can act as a grid following or grid forming. Sorry? No, I'm saying that it has this possibility. So for example, if you have a microgrid, you cannot use the grid following because we have no grid to be connected. We need grid forming, okay? But if you have a grid supporting, it can work as a grid following, which we are in the grid connected mode, and it can also work in a grid forming when we are in isolated mode. So this is the difference. But when we are talking about the grid following, it works only, yeah. So now we get back to this one. We said that it is a DG, but it is not microgrid. Why? Because the converter we have here is working as a grid following. So when we don't have actually grid here, in fact, it cannot work, and then so it cannot shape the microgrid in the system. So now, if I ask what is the difference between these three configuration, 100% of you know, yeah? Where's the area? Okay, he's not. Abe, is it clear for you? If I ask you to come here and explain what is the difference, you can, yeah? Grid forming. Okay, this one. Okay. So now we know what is the difference between grid following and grid supporting. So now grid forming. Grid forming is a type of the converter or conversion system which can react as a voltage source. It means that it can create the own voltage and frequency. Okay? The difference from here and here is that they are following the voltage and frequency from the grid. But this is separate. So if you are going to, for example, create a power for 60 hertz, you can do it. 50 hertz, you can do it. 45, you can also do it. Okay? But for this case, you make the measurement from the grid and then tune the operation of the converter and react based on that. So if the grid current is or voltage is 50 hertz, it can create the 50 hertz because it measured the 50 hertz. So this is independent from the grid, but they are dependent. But in the case of the grid supporting, it can be also independent. So, clear enough? Mm-hmm. No, in grid supporting is the best application because it can work in isolated and grid connected mode. Grid forming cannot work in the grid connected mode because I mean, you can actually, but there are some synchronization, so you need the PLL. But the mission of this type of grid forming converter is we remove the PLL because PLL provides some actually is sensitive to the disturbances and yeah.
So you are indicating, sir, afterwards that we will have a grid supporting system. Initially, it will act as grid forming when the system is connected to the
Yes.
system and grid forming.
Yeah. So this is also a good point that I'm going to repeat again. So in grid supporting, we use for the microgrid because grid supporting is able to work in both grid connected mode and isolated mode. Siddhant, did you get it? Do you remember what is the grid connected mode and isolated mode? No. So how is possible you get it without knowing that what is the... Okay, so let me explain again one time more about the grid connected mode and isolated mode. So this is our microgrid. So microgrid is a part of the grid which can disconnect it from the grid when we have some problem, and then we can return back to connection mode when problem is solved. So if you look at here, we have this static switch. So it means that we have actually some loads, some generation, so it can make the balance between the generation and consumption by energy management system. So then if some problem happened, we can be disconnected from the, so it means that we are in the isolated mode, okay? But when we connect to the grid, we are in the grid connected mode, okay? So now we get back to here, we see that we have three class of the conversion system. So grid following means that we follow the grid. So if grid frequency is 50, it's 50. And the idea is that we inject the power. So if you are committed to, or you have a small power plant, you are going to sell your electricity to distribution company, your responsibility is provide the electricity you promise it. But when we get back to grid forming is a type of the conversion system which create the voltage and frequency. So if you are over a mountain, so you are going to provide the electricity for a single load. You don't need to create the actually transmission line up to over the mountain. So you can use the grid forming conversion system and create the small grid with the frequency and voltage you need and support the load. For grid supporting, it can work both in grid connected mode and isolated mode. So if we have a microgrid, it can actually be disconnected from the grid and provide electricity. So this one acts as a grid forming like this, because it's like a source and load, that's all. But when it's connected to the grid, it can be grid connected mode because it should follow the frequency. Yeah.
Sir, grid farming is going to establish the grid according to their configuration,
Yes.
where it is not dependent on the other grid like power sector everything.
I mean, basically, it can be for the grid forming, you're saying, yeah? Yeah, for the grid forming, you can actually set some points that it provides some support to the grid. But the main idea is to provide the power to the grid. But if you set the point and set that, for example, if we use the drop controller and then we set the point between frequency between 90 to 51, then it can balance the voltage and frequency based on the active and reactive power injected to the grid. Okay? But we will see how it works. So now it's important that you get the difference between these three categories, because lots of people make the mistake between the grid supporting and grid following, or grid connected and grid following converter. So this is the structure for the grid following or grid feeding power converters. So basically we have actually, the model is working like a current source with the parallel impedance, and this impedance is quite big. Does anybody knows that why it is big? Why?
The impact of the grid is consider the transmission line as well as the capacitance between the transmission line.
But transmission, you cannot, yesterday I discussed that, you cannot connect the converter to the transmission line. You should use the FAC devices. Yeah. The idea is that, for example, if you have a 1 ohm impedance, and then you parallel it with another 1 ohm, so the equivalent will be equal to 1 over 2. Okay? But when you have 1 ohm and another is 100 ohm, is 1 times 200 plus 1 plus 100 is near to 1. So the impacts of this big impedance is not that much when you are working in the parallel connection, so it doesn't provide too much losses for the system. You can ignore it. So this type of actually system are working like an ideal current source, and we can also provide somehow power for the services, power for the grid by injection by integration from the renewable energy source. Basically, we use the current control for this one, but the problem, not problem, but the requirement is that we need to have the voltage and frequency from the grid. Yesterday I said that for this case we use PLL to measure the frequency and an instantaneous angle of the grid, and based on that we can tune the controller and provide the electricity to the grid. And one important thing is that we use the PLL to know the instantaneous angle of the grid. So what is the meaning of instantaneous angle of the grid? And why do we need it? Does anybody has any comment about this? Why do we need it? So assuming you have this grid, three-phase system, you're supporting load, and you're going to connect your converter here. So this is three-phase, 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 okay? So we said that we need the PLL to measure the V1, V2, V3, and give it to PLL, and we have omega and theta. So V1, V2, V3. So what is the benefit of this such measurement. Why do we need it? Is important. So, yeah. And when the grid is stressed or is faulted, then we can provide the electricity actually from the generation for the local load. Okay, is it clear up to here? So, but assuming that you are going to, for example, supply by these storage devices, you have a DC AC converter. This converter should work as a grid uh, supporting, okay? Because it should be able to create the voltage and frequency we need. But the difference from this one, from the and grid forming converter, is that this converter is following the reference based on the grid. So if grid is disconnected, but the frequency was 50, it has information that the frequency is 50. Okay, but in grid forming, you can form it. You can say that the frequency is 70, 60, I don't know, 40. You can decide based on the demand. Okay, so by this, when we return back to the grid connected mode, again it works like a current source and provide actually power to this bus. And if you have extra power, we can also consider for the grid. Yeah. But the difference is that in grid forming, we don't need to have the PLL. But in grid supporting, we need to have PLL. Yeah, this is the difference between these two technologies when they are working in isolated mode. You mean from the grid connected to islanding mode? So we have this static transfer switching, static STS, static transfer switching. So it detects the voltage and frequency of the system, the network. And if we pass this limitation, the border of the limitation, it means that we have the problem in the grid. So for example, if short circuit happening, we have the voltage drop, and you can see that there are some problems. So it is better that we get, otherwise our system will be, our load will be damaged. Okay, so basically based on the monitoring, but there are some other techniques. So for example, you can get the information from the distribution company about the price of the grid electricity. So it depends if you are going to maximize the benefit from customer point of view. In fact, you can be disconnected from the grid and operate in islanding mode, because you can provide electricity by yourself for your load. So there are two different points: grid point of view or customer point of view. Is it clear? Good. Any questions so far?
Coming to the supporting part, can you come to the
You're taking this one?
grid supporting?
Yeah. Okay.
That T diagram,
Mm-hmm.
suppose if the reference power increases,
Mm-hmm.
then actual power also has to increase.
Yes.
Summation.
Yeah. Here you mean?
Is that summation true or deduce or subtract?
Basically, this is based on the group controller. Okay. So they said that delta frequency is equal to C or K or something times to delta P, or delta P is equal to Cp times to delta omega. So it means that when we have the changes delta F, so delta F is the frequency changes. So you have the reference in 50 hertz. So your reference frequency is constant, okay? But what you consider as a grid frequency is something different. So assuming that your grid has some event, and the frequency change between 90, 49 to 51. So you can define delta V between 49 up to 51 is fine. But when it goes to less, like a 48, then it works. So delta P should change because P is a constant value. And then they said, for example, now I inject 10 kilowatt, but the frequency drop. When the frequency drop, it means that we need increase the active power to return back frequency to this actually borderline. So by this, you increase the actually value of the active power, then compensate the frequency of the system. And for the reactive power is also the same. So later we see, I mean, I didn't go through the mathematical equation, but later we see that equations that, you know, when we have delta Q or a reactive power change is equal to a constant value times to delta V, because we can control the voltage based on the reactive power. So for example, we easily said that the voltage runs between the, I don't know, 5% is okay. But when you pass the 5%, so it means that you have some problem in the reactive power of the system. So you should increase the value of the reactive power injected from the source to the grid. So basically, it can be somehow, because the power injected from the converter to the grid is a constant value. But in the fault time, when we have the problem in voltage and frequency, you can play with the active power and reactive power. So, for example, 10 is equal to so in converter S is equal to P plus JQ, okay? So, for example, 10 is equal to 6 plus J8, 10 is equal to 8 plus J6, okay? So, it means that the active power can be 6 or 8. If the frequency is dropping, we can increase the value of the active power. And if the voltage is dropping, we can actually increase the value of the reactive power. So this is the difference between grid connected mode and grid following mode. In grid following mode, they don't care. They said that this is my commitment, I should inject 10 kilowatt. What is happening in the grid is not my business. I have some commitment to provide that much electricity for the grid. But in the grid supporting or grid connected, the main idea is that to regulate the voltage and frequency by injecting. You can inject active and reactive power basically when we have no problem, because the main idea for integration of renewable energy is the injection of the active power to the grid. But only active power is not enough for the stability, so we should provide the reactive power. But the share of the reactive power is much more, less than active power. So just a simple example in this Autocom project, they have a unit with 1 megawatt active power, but they had also 50 kilowatt reactive power. So the idea was the injection maximum active power, but the reactive power is also needed for the stability of the system. But the difference is active power is 10 times to 20 times more than the reactive power. Okay? You got the point? Okay, good. Any question? Yes.
In basic circuit theory, we have studied a current source can be converted into voltage.
Yes.
Here we can convert this.
This is also the same assumption. because it's possible to play. But what we are discussing in circuit theory is the equivalent with the Thevenin model and Norton model. What I can say, it's dependent to the control operation. So in this operating condition, we jump from the current control mode to the voltage control mode. And the difference between this technology and grid following converter is that in grid following converter, we just follow or we control just the control of the current. But here we have the combination of we have a two-stage. We have inner and outer control loop. So in first stage, we provide the current control loop, but when we jump from the connected mode to isolated mode, it jumps from the current to voltage control mode. So this is we have the two stage of the control, but in that we have just one stage of the control. Yeah.
In mathematical model, can we convert them?
Yeah, I mean, as long as we are researcher, I can say yes, we can, but you should decide to go forward for that or not.
Which component is responsible for jamming?
Which component?
Parallel jam.
That one. Basically, when we are talking about, but you should tell me clear that in which mode. If you are talking about the, for example, power plant, or you are talking about the small.
How we can decide this is act as control current source or that is voltage source?
Yeah, I'm saying that if we are in isolated mode, we go to the voltage control mode because we have no voltage reference. But when we are in a grid connected mode, because we need to be synchronized, we get the information from the grid and it goes to the current control mode. And later you see that why we should do it. Do you have any other question? Okay. Because do you know what is this QP? I mean, the Clarke transformation and how we can control the converter?
This is only for the comparison
Mm-hmm.
purpose.
Mm-hmm.
We can convert LDC to C2 transformer.
Yes, but we need the theta, okay? Because we have this Clarke transformation which is based on the theta, and this theta is coming from the grid. So when you get the grid theta, it means that you control the converter based on the theta from the grid. So anything happen in the grid, you can see in the control loop of the converter. Then the converter can react based on the situation of the grid. This is the reason. Yeah. So, any questions so far? Is it clear for you? Okay, when you don't say anything, I really don't know it's clear or it's not clear. It's clear, good. I mean, it's a basic. If you say that it is not clear, so what should we do then later? Okay, Arya is not here, yeah? Tell him that it was biggest lose of his life. Okay. So now we get back again the characteristic of grid following converter. If you see that we normally use the PLL for that one when we are in grid connected mode. So basically we can regulate the active and reactive power of the system based on the control of the active and reactive current. And just we cannot say that active current or reactive current. But later we can see that, you know, there is because the voltage is constant or must be constant, then the active power is somehow related to the current, and reactive power is also related to the current. So this is why we said that, you know, they are somehow controllable based on the control of the active and reactive current. So in fact, we can control the P and Q based on the current. So we also have the current set point. It's somehow calculated based on the needed value that we need for the regulation of the or the injection of the power. So we cannot say that this is our system. We can actually inject whatever you want. You need to provide the set point, and based on that you can inject. So the simple example is the Atacama project. I mentioned that we have 1 megawatt active power, 50 kilowatt reactive. So it means that the converter is responsible to inject that much active, that much, because the set point is for that one. And mainly this happening when we are actually in power plants. It is very important to consider that one. So, any questions so far? So if you consider the structure, always it's follow based on the actually PLL, the theta getting from the PLL. And there is some problem because when we go through the PLL, then if fault happening, then the control loop get in the problematic situation. So we need to consider also some extra feature in the control loop of the converter. For example, if the fault happening, the fault right through capability is something we should consider in the control loop of the converter. So for this reason, only considering the current control loop for that types of the converter is not enough for the power grid. You have one option to just inject to the distribution power station, and after that, or if you are going to connect to the load center, then you should consider some extra feature is also needed. Look. Any questions so far? No? Okay. So this is also the other part. I mean, we somehow consider the active and reactive power injection by controlling the voltage and phasor amplitude. So at the point of common coupling, and the reason for this grid forming technology, which we consider based on the PLL, is that based on the grid is, does anybody knows? We said that we don't need PLL, but in reality we should consider the voltage and frequency of the grid for the grid forming converter. So does anybody know why? We can say that we provide power based on the voltage and frequency we need. But now we can say that based on the point of common coupling. So common coupling means the grid, the point that converter is connected to the grid. Does anybody knows that there is some contradiction? Yeah? Does anybody knows why? What? I mean, one thing is the grid code. Yeah, you cannot be connected to the grid. Does anybody knows what is the grid code? Okay. No, grid code. Grid code is some actually rules that the country define. So they said that you can, for example, provide electricity, but for the connection to the grid, you need follow some rules. So this is why the Chinese said that you can provide electricity for yourself, but you cannot inject to the grid. Why? Because it makes some problems. So grid code said that if you are going to, I mean, basically any component with, it can be trans, it can be converter, it can be anything that you, but you need to actually follow the grid code. So, just a simple example. Grid code said that you can provide electricity and integrate to the grid if the THD is less than 5%. So it means that your power should have the high quality. And if it is 6%, it means that it is not in the standard that we are actually we need. So for this case, you can actually generate it, you can use it, but you cannot inject to our grid because our grid standard is less than 5%. Okay, so this is the something that you need to follow. And the other thing is that you are going to create a power plant, and we said that we use the grid forming converter. Then the grid forming converter should follow the grid. It means that the grid has the situation at the end you are going to connect this power plant to the grid. So it is good to follow the grid in the right one. This is why that when we have actually like a multiple system, it is better that we have a synchronization with the grid. There are some other actually technology that you can be synchronized with the grid without using the PLL, but the best is that we have reference from that. Any question? Okay, good. Harmonic? THD 5%. Yes. No, current is different story. And we are not talking, because current is returning back to the customer side, and customer is normally non-linear. It can be, I don't know, 20, 25, anything, okay? Yeah, but in the ideal situation, customers are not also connecting non-linear load to the grid. Okay, this is why actually distribution company give the penalty to them. Okay, but in power quality, yesterday I talked, when we are talking about the power quality, in fact, we are talking about the voltage quality. So at the end of the day, if you are going to provide electricity to the grid, it should be both the THD of the current and voltage should be less than 5% THD. But in the load side, we are responsible as a DSO to provide the voltage less than 5%, but the current is dependent to the customer side. Okay? Udaya, did you sleep well last night? Yeah, I feel a little bit sleepy. Yeah, okay, good. So, sit down. What happened after dinner? You went to party or you? Okay, yeah, seems that you are sleepy now and the other guys are not. Okay, now I got the point. Okay. So you're touristic visitor student. Okay, good. It's one shot for 3 targets. Okay, good. So, any questions so far? No. So now we are going to talk about we talk about the 3 class of the conversion. And if I'm going to tease your coordinator, Mr. Udaya, then he's going to one time forever actually repeat that what kind of technology do we have. So I'm talking about these 3 things. So tell us, Udaya. Grid forming, grid following, grid connecting. Yeah. What kind of classification we have for the conversion system? Mm-hmm. Mhm.
DC to AC or AC to AC. These
Yes.
are the four types of
Yeah.
converters.
Yes. Yeah, we have three. This is something that I emphasized at the beginning, and Odaya answered my question 100% correct. I said that what kind of conversion system do we have? He said that DC-AC, DC-DC, AC-DC, and AC-AC is 100% correct. And then uh, just the idea for asking this question from Udaya is that because he was absent, and I'm going to make sure that you understand this type of technique is the conversion system, is not the class of converter, okay? But they normally said that classification of power converters. So, based on this topic, they said that the answer is 100% correct, and thank you for precise answer. And but you, when we say that grid forming converter, grid forming converter is not the converter, is a conversion system. Okay, so converter can be normally just conventional two-level converter, but it is controlled in a way to react as a voltage source. So later, if someone asks you, what is the grid forming converter? You said that this is the type of the conversion system which act as a voltage source. And what is the grid following converter? This is the types of the conversion system act as a current source. What is the grid connected? It is the type of conversion system can act as a voltage or current source in the network. So now it was the introduction of this conversion system. Now we are going to talk about the Clarke and Clarke transformation. So how many of you guys know that what is the Clarke and what is the Clarke transformation system? Just raise your hand. 1, 2, 3, 4. Okay, good. I'm pretty sure that you know it. You know it. You're trying to say that I don't know it. Yes, they know also, but they are tired. Yeah, okay, so, yeah. So, Udaya, you don't know, yeah? Okay. So, okay. Anyway, so we have actually Clarke transformation is a type of actually transforming from 3 dimension to 2 dimension. So we have A, B, C. Okay, by this matrix, we transfer it from A, B, C to DQ. Okay, just look at this one. When the angle change, look at this angle. When the angle change, because the voltage is changing from the 0 to 360. Okay, when the angle change, the position of D and Q change. So, but this position is not somehow, the value of the VD and VQ is not the constant. So it goes up, down, and they follow based on this equation. So if you have a function in ABC, so you can times to this one and provide the DQ. But if the system is unbalanced, we have another actually point, we call it 0. So it can be another 3 dimension matrix consists of D, Q, 0. But in this course, we are going to talk about the DQ. So we have a constant value 1 over 2, 1 over 2, 1 over 2. So assuming that you have VA, VB, VC, so VA, VB, VC. So if you times this one to VA, VB, VC, so at the end of the line, you see that 1 over 2 times 2 V0 is equal 1 over 2 VA, 1 over 2 VB, 1 over 2 VC. 1 over 2 VA plus VB plus VC. What is the value of this? In balanced system, VA plus VB plus VC is equal to 0, so it is equal to 0. This is why we convert it VD, VQ, and this V0 is equal to 0 in balanced system. Any questions so far? Now the question is that, okay, we are going to change it from A, B, C to DQ. What is happening? Why we should actually eat the food by this way? Is there any benefit for us? Is there any food? Yes, it is. Okay. Does anybody has any? Yeah. Why control will be easy? We change from 3 variables to 2 variables. Okay. Good question, good answer, but it's not complete. Siddhant, do you have any idea? No. Okay. Sorry? Exactly. This is what I'm looking for. Thank you. So when we change from ABC to DQ, so first that we change from 3 dimension to 2 dimension, and second, if you look at here, we change from sinusoidal to the DC value, and then, so let's go to the next part. If our input is this one, A, B, C, the output will be constant value. So assuming that you have actually a system with the harmonic, and you change it from ABC to DQ, so the fundamental frequency become DC value, and the harmonic frequency will be something else. So by use of the filter, you can actually separate the fundamental frequency easier from by harmonic, and then you can make the compensation in the control. So for example, just a simple example. So assuming that this is my converter, DC AC converter, and this is my source, and this is filter, and this is load. So I'm going to compensate or provide the electricity from this source to this load. So this is I load. So I said that, okay, I get IL1, IL2, IL3, and convert it to ILD, ILQ by Clarke transformation. Okay, up to here is just a transformation. Then I said that my load is somehow nonlinear. So then it can be split to 2 parts. If I draw this one, ILD can be fundamental frequency and harmonic. I said that when we change from ABC to the O, the Q, the fundamental frequency in DQ will be DC value. So this is my DC value, but the harmonic is harmonic. Then I use a low pass filter, then give this ILD and just get the fundamental frequency as output. Okay? And I just make this one fundamental frequency, and this is ILD. ILD plus minus. So what will be output? Harmonic. Okay? So now I use this one as a reference for my converter. I say that, okay, this is I harmonic, and then please compensate the harmonic. Okay? So the rest of the load will be supported by the grid. So harmonic will be from here, fundamental frequency will be here. Yeah? So IL is equal to I fundamental frequency plus I harmonic. I harmonic is coming from converter. So fundamental frequency is coming from here. You see, the control will be extremely easy for us when we transfer from ABC to ODQ. And then another benefit is that you can actually split the currents to different, I don't know, harmonic, reactive power, fundamental frequency, and you can inject the maximum available power. So based on that, you can prioritize that, you know, if your system is going to compensate the reactive power or harmonic or active power. So different applications, we can play with the reference and provide different services. So now I'm going to simply ask a question. Assuming that you have a company, that the company has a lots of nonlinear load, do you believe that you can support these loads from the grid? You. What is your name? Ash? Rakesh. Okay, Rakesh. It's quite easy. Rakesh? So, next targeted student. Rakesh, do you have any idea that we can connect this nonlinear load without any problem to the grid? Yes or no? Yes. Very simple political answer. Yes. Yeah, definitely we can actually, because we need to supply the load, Rakesh. Okay. So then we get back a little bit this side, in the grid side. So assuming that you have a power plant and this is in the Atacama Desert, and I said that the idea is that we provide the electricity from solar, and each unit can provide 1 megawatt active power and 50 kilovolt ampere reactive. Yeah? Reactive power is actually for the stability of the system. This active power is in fundamental frequency, if I'm not wrong. Yeah? You provide electricity with the 50 hertz and the voltage PhD less than 5%. So how is possible? Your system is nonlinear, you need the nonlinears, but your generation is linear with the 50 hertz. What is happening between? What?
Reactive power compensation like that.
Compensation.
At the load end, we have to provide reactive power compensation. Like
But I'm talking about harmonic, not reactive power. Okay? But now my question is that it's a little bit confusing, yeah? We have a nonlinear. Rakesh said that we can connect it, but I said that I don't have actually harmonic, so what is happening? So it means that you make some disturbance for the grid. Am I right? So then what is happening? Then the distribution company said that, you know, no, you are not allowed to be connected. You should compensate your system, your load. Otherwise, you should pay 10 times penalty, because you make the grid unstable and then it affects the other loads also. So you cannot. So what should we do? Now, for example, we have actually very smart uh, expert engineer. What was your name? Ross. Ross is also easy. Rakesh Ross. Okay. So, Ross, what is your solution for this one? Okay, you're not listening me. Now, I'm saying that, do you have any solution to solve this problem or not? You prefer, as the owner of this load, pay 10 times penalty, or you use a smart. If my father was like this one, he fight with the distribution company and said that if I pay 100 times more, I will not actually change my system. So it is not a smart solution. Okay? But do you have a smart, cheap, a smooth solution for that one? Compensation. This is also, they are very actually good to be lawyer, something. Yeah, compensation, yeah. Mm-hmm. Yes, I agree. So, but now I'm talking about the harmonic. But yeah, you're right actually. Power factor is also one important factor that after that we will discuss about that. Yeah, like filters. What kind of filter? Passive filter, active filter, low pass filter, high pass filter. Which? What? Active for excellent. Active power filter. Active power filter means that we provide the harmonic part of the load, and then the linear part can be compensated by the grid. So I can say that, okay, so I'm owner of the company. I don't like to pay penalty, and Ross is a very excellent, super intelligent expert in this concept. I get the idea that how we can solve the problem, and he said that, okay, so I'm expensive, so you should pay 5,000 euro. I will check it for you and fix it for you. So I use actually a local power generation. So in the corner of my company, I set the PV or storage devices, and then compensate the harmonic by this system, and then the grid can be free of harmonic. So we can provide harmonic from the local power generation. So the reason for this question is that you can change the controller based on your actually demand. So in this case, you are going to use this one for the harmonic current compensation, as Rose said, the compensation. But as Somi also said that, reactive power. In some cases, you have the reactive load, which change the power factor of the grid, and distribution company again ask you to compensate it. Otherwise, you should pay the penalty. So for this case, in the conventional technology, they use this capacitor bank to compensate the reactive actually power in the load side. But the smart solution nowadays is that we use this technique. It means that we just provide the reference from IL, and then split it to ILD and ILQ, and later we can see the ILQ will be reactive power and ILD will be active power. But it is not always like this. It depended how you calculate it. You will see it. And then I asked the converter to provide the reactive power based on this reference. And based on this, we inject just ILQ, and ILD is coming here. It means that reactive power is coming from the converter, active power is coming from the grid. So it means that this is power factor is equal to P2 plus Q2. So when Q is 0 in grid side, so power factor will be equal to 1. Okay? So all in all, you can tune your converter and based on the demand, you can control it and get the maximum benefit. And there are another option. So the first option was the active power filtering. So we call it active power filter. It means that we compensate the harmonic. This one is the power factor correction. So if you have extra power, you can merge all of them. You said that I'm going to compensate the harmonic, active power, and if we have extra power, then we can also provide some part of active power in the fundamental frequency. We see later. Udaya, you want to have some break? Seems that you're tired. Yeah, okay. Good. Okay. Main objective be using the Clarke transformation. There are some drawbacks also we can see later, but as we are engineer, we should be happy as long as we have the problem in the system. It means that we can earn more money. Okay, so you should be happy. And one mission of the engineer is that when you finish the first problem, it is the starting point for the next problem. Okay, so your life is like this. Yeah. So we learn by this one. Okay, so if you reach in the point that you feel that you solved all the problem of the board, it means that you should not be too much happy for that one. I sent the paper to IEEE Transaction Industrial Electronic, and 5 of them answer positive, but with some comments. Then 3 of them accepted after first revision. Then I noticed that one of them gave a different comment again, new comment. And then I answered that one, and number 4 accepted, but number 5 give another new comment. And then I answered to this one, and he provide, because after 2 rounds, they should make the decision, but they provide again new comment. I said, okay, so this project, this paper will be rejected. So let me write something harsh to them, then they reject, and at least I feel a little bit more happy. So I said that, sir, do you believe that the controller you're developing should solve all the problem of the board? And then editor-in-chief actually make the decision, as you mentioned, this is correct, your controller cannot cannot solve all the problem of the board, so your paper is accepted now. So yeah, it was very logical actually. Anyway, so if you reach that point, you shouldn't be happy. It means that you cannot learn new things. And one thing I can promise you, as an engineer, if you learn how to control the converter, always you have a good opportunity to get a good job. It's not something that, after 5 years you have no, because this is a roadmap for the countries, for all countries, that to reach the carbon neutrality by 2050. I don't know, do we have some roadmap in India yet or not? 2070. Yeah, 2070. Yeah, it makes sense because, it's a big country, and then, when we reach, we think about the 2070, it doesn't mean that, we reaching the point probably in 2035, we reach that, renewable energy probably create more problem for us. It's possible. We start to integrate the renewable energy before, I don't know, in the beginning of 2000. Then when we reach 2009, 10, we noticed that when we increase the level of the renewable energy, we have the instability in the frequency of the system. And then they noticed that this is due to the lack of the inertia. So when we reach 2020, they define the grid code that you are not allowed to integrate your converter to the grid if you cannot provide the inertia for that one. And in 2022, 3 something like, they have some project that they claim that if we provide 1.5% based on the 10% increment in the renewable energy, the share of kinetic energy should be 1.5% to keep the stability of the system. And then nowadays, again, we get the problem that, you know, this type of technology is not, we cannot actually store it, and the temperature and the radiation, the speed of the wind, they are not constant, so it provides a dynamic issue for the grid, so it is better that we use the hydrogen technology. And then now we said that, okay, hydrogen is not that much fast. So we need to provide another technology to provide also fast stability compensation for our system. And the other is that, you know, we have a very less efficiency. So for example, when we use the wind to electricity, the efficiency is 85%, something like this. But for the hydrogen, it's between 10 to 22%. It's very low. So this is the problem. But the good news is that as long as we have such problem, we need the people to work to solve this problem. So the job market will be also good for us. So I can say that it is better that you learn this one with me or without me, then later you have actually good chance to get a good job. Okay? Siddhant?
Yes, sir.
So you feel sleepy today? Yeah, I noticed that. Okay. And Rakesh, okay. And Rose. Oh, my friends are growing actually. It's an equivalent of the integration of actually increasement of your penetration of renewable energy and penetration of Indian friends in my my list. Okay, good. It's always pleasure to have Indian friends. Okay, good. Now we talk about this park transformation. It is somehow very useful. There are some drawbacks, but there is also some good solution for that one. We will see later. But there is another useful tool. I mean, we don't consider this one as a controller, as a, I don't know, nothing. This is a tool. That's all. You can use it or you can use something else. Okay? So, we have another so we have another transformation. Actually, we say it Clarke transformation is also the same, but the matrix thing is not the previous one. We have actually theta. So theta is changing, but in the time we have actually a constant. We have it's constant. But for the next, we have just a constant to the sinusoidal value is a sinusoidal value. The dimension is changing, but we have this possibility to convert from 3-dimension to 2-dimension. Again, if you have an unbalanced system, we have alpha, beta, 0. Okay? So this is the reverse one. So we see that, you know, the 3-phase can be changed to the 2-phase, but with the sinusoidal and different amplitude. So in each time when the theta is changing, the value is changing also. So the benefit of this is like a complementary side of the DQ, but there are some benefit in alpha beta in comparison with the DQ, but DQ is more flexible because we can separate the fundamental frequency with the variable frequency, and then compensation is much more easier for us. But Up to here, there is nothing behind of this technology. We see that, okay, this is a matrix. We change it from 3-phase to 2-phase. And then we use later for the controller. And if you don't know where we can use it, you don't know it, this is not you shouldn't be worried, because this is part of our class. So now we get back to what we discussed as a beginning. We always said that we have a grid, we have